Next one is closure. Closure is a function which has access to a non-local variable, which is also called a free variable. So if you have a look at this code, here is a lambda expression and it has access to a non-local variable called today. This is a non-local variable to this lambda expression because it stays outside this lambda expression. So this particular lambda expression is closure because of that. And let's just think about what we had before Java 8. For closure, we had an anonymous class. So what I'm going to do here is creating runnable object using anonymous class. So to make it closure, what I'm going to do is declare local variable of that main method. So let's call it number and put 10 there. And what's inside is, it just print out the number. So to see the result, run it. I should get 10 and I got 10 as expected. This is a closure before Java 8, and it is not fully closure because to make it this non-local variable accessible by this runnable object, this one has to be final. What about then lambda expression? Well, it's slightly different, but in a sense it's actually the same. So let's just do the same thing using lambda expressions. So I created another runnable object using lambda expressions, and it does exactly the same thing, and I should get 2 10s. Yeah, I got 2 10s, right? So for lambda expression, let's just forget about this runnable. This anonymous class object. So to make this non-local variable accessible by lambda expression, this one has to be either final or effectively final. Effectively final means if you use non-final variable like a final variable, that is effectively final. Well, by using non-final like a final, once you initialize that non-final variable, then you never reassign anything until the end of the block where you declare that variable, then that's effectively final. So as you can see, once I initialize this number with this value 10, this int value 10, I've never reassigned any value to this number, in this block, right? Then it's effectively final. Which means if I put any value, if I reassign any value there, doesn't matter it's before using lambda expression or after, I immediately get this compile time error. It says local variable number defined in an enclosing scope must be final or effectively final. Okay, so it doesn't matter if it's before or after. Okay, I get the same error, right? And so just get back to this slide. So as I just explained, to make this non-local variable accessible by lambda expression, it has to be either final or effectively final. So final case, everyone knows, right? It's just like using an anonymous class object. And effectively final means you use non-final variable but never reassign anything until the end of the block where you declared that variable, then that's effectively final. So lambda expression can access that variable. And this case is not effectively final because once I initialize this this variable today, I reassigned an instance of this local date time to that today variable. So it is not effectively final, you get compile time error. And in Java 8, to keep the consistency, this anonymous class object can access that effectively final non-local variable. Okay, just like lambda expressions. So why does it have that restriction? About 4 years ago, in 2010, there was debate going on, in the Java in the mailing list for project Lambda, and that time, Brian Getz, a Java architect at Oracle, announced the state of the Lambda, and there he talked about that matter. So if you have a look at this, he said that because of possible race conditions, to make this non-local variable accessible by lambda expression, it has to be either final or effectively final. Okay, so multiple threads access a single resource and try to modify it, then race condition can happen. If multiple threads access a single resource and it just read that resource but it doesn't write anything, then race condition doesn't happen. That's why this one should be final, which is read only. Okay, and the time Neil Gafter, who was also working on another kind of closure, didn't like that and complained about it, and he said that designing a language feature around one particular category of use case generally results in a poor language feature and a need for further extensions. And he also wrote about that matter on his blog, and it's actually he wrote long ago, like in 2006. So if you like, you can visit the link and read it, and I'll put the link to access this page on my blog. Okay, so you can read it. If you after you watch this video, if you visit my blog, and you can see that. And also I recommend his talk on evolving the Java language, and this one about the closure. Okay, these are good ones. So yeah, these are the videos I also recommend. Okay, it would be fun to watch. And yeah, this one. So if you visit my blog, you can find all those links, and any source code I showed in this video you can find. All right, so because of the race condition, it has that restriction, so it has to be final or effectively final. Okay, so effectively final means you just have some conciseness, but it's actually it has to be final, like you use it as final. Okay, all right, then you may think, well, if it's the same as the old way, then isn't lambda expression just syntactic sugar? Well, it's not just syntactic sugar, and there are several differences, and I'll tell you what. So let's think about this keyword in anonymous class object and lambda expression. So if you use this keyword inside anonymous class, then this means this anonymous class object, right? Okay, but in lambda expression is lexically scoped, which means its scope is extended to its enclosing scope, meaning this keyword here is enclosing class instance, not this lambda expression itself. Okay, so I'll just show you some example. So for example, let's just comment it out. Here, if I do this toString, if I call that toString method, and what happens is this toString method is actually toString method of this runnable object. So I'll get toString method of this runnable, the result from that toString method. So if I run it, you just comment out this part, lambda expression, run it again, and as you can see, it has app2 $, then 1. Well, this means this runnable anonymous class. To prove that, what I'm gonna do is I'm gonna override this toString method of this app2 class. So here what I'm gonna do is I'll put here I'm app2 like that, and then run it again, and I didn't get that, which means it's from there. So how can I print out the toString method of that one? Oh, before that, let's just think about yeah, you may think putting this, but as I said, this means this runnable object. So I get, actually if I do this, I get the same result, right? Like that. Okay, comment out again. Yep, same result. So to actually run that toString method, what I need to do is app2 dot this dot toString. Okay, but well, I got error. Why? Oh, I cannot actually call that method, right? Because I have this runnable object inside this main method. It is static. It is static method. It doesn't belong to the instance of this app2, so I cannot do that. Sorry. Okay, I'll show you later. So if I do this, and it prints out that this result of this method from this runnable object. And what happens here? If I do, okay, let's make it like this. Put the block so I can have many statements. So here, what I'm gonna do is same thing, toString. And what happens if I do this? I should get a compile time error. Comment out. Yep. Typo. Okay. Yep. Why? Compile time error. Why? As I said, this one is lexically scoped, and this lambda expression is actually having just method body. It is like an anonymous method. It's not like that anonymous class object, so it doesn't have a toString method, right? So if I try to call toString method, because it's lexically scoped, it tries to run toString method of what? Of this app2 class instance, and there is no app2 class instance because I declared this lambda expression inside this static main method. So to test this one, to make it work, well, of course this one doesn't work either, right? Because there is no instance of this app2. So to make it work, I need to put it in some instance member method. So private void test, like that. And here at the end of this main method, what I need to do is I need to now create an instance of app2, then run that test. Then what do I get if I do this? Okay, let's just forget about this part. Okay, what do I get if I do this? I get I'm app2, which is from that app2 class object. Alright. Oh, I forgot to run it again. Yep, I'm app2. So this is not from lambda expression itself, but it's from that enclosing class instance. Okay, what happens if I do this? This doesn't mean, as I said, this doesn't mean this lambda expression, but enclosing class object. So run it, same thing, right? Okay, so let's talk about more difference in this context. So what's the difference between that anonymous class and lambda expression regarding lexical scoping. So here, if I do, for example, inside, okay, let's just put some instance member variable. So I want to put here private, same thing, int number, and put 1 there, right? And here I have 10 inside this main method. Okay, to test it, I just need to put it in some instance member method. So put it inside this test. And okay, here I have member variable 1. Here I have a local variable of this test method number, and it has 10, and here I print out that number. Then what happens is it should get the closest one, which is 10, and if I do the same thing here, yeah, I should get the closest one, which is 10. So I should get 2 10s just like before. Yeah, I got that. And let's just think about this anonymous class case here. What happens if I want to print this number from this app2 class object? What I need to do is, I cannot do this as I already already proved. Well, I have compile time error. Why? Because the runnable doesn't have any member variable called number. So what I need to do, like this, okay, and I can print it out, run. Okay, I got 1 from here. And what happens if you just do this? Okay, then again, what happens if I declare that local variable of this run method having the same name as no local variable number? Okay, what happens? Well, if you have anything has the same name as any member of this enclosing class, then it shadows that one from enclosing class. So if once you do this, you have no way to access this one. Okay, because because of this one, it shadows that. All right. Okay, so if I do this, obviously I get 100. What about 1? Yeah, you can still do old trick. So 2, this, and it prints out 1, right? But you have no way to access this one. Okay, you have no way. And then what about lambda expressions? Well, it is lexically scoped, so if you do this, well, obviously it prints out that 10, right? And if I want to print out that number from this member variable, then I just need to do this. And this, as I already said, means this enclosing class instance. So run it, I should get 1, right? Just like that. And what about if I declare the same, variable with the same name? What I get is compile time error. Why? It's lexically scoped. As I said, it's scope extended to its enclosing scope. So it is same as you're having 2 variable in this scope having the same name. Okay, it is just like that. All right. So that's why you get that error, compile time error. So you cannot even have it. All right, which means there is no way to shadow that local anything from this app2 class, enclosing class. You cannot shadow that non-local variable to this lambda expression. You can't even shadow that any member method. So for example, if you have a look at this code here in this anonymous class object, think about this. What happens if I do this? Yeah, you've already seen that it calls toString method of this runnable, right? Okay, like that. And what if I want to call this toString? Yeah, you know that app2 dot this dot toString. It prints out I'm app2, right? Okay. Then what happens if this app2 has static method called toString, and it takes some string value, let's say name, and then what it returns is hello, and then plus the name. All right. So if I want to run that, okay, you may think like this. Okay, I want to run that toString method. So there is only one toString method taking that one parameter, which is string. So I can just call it here. I put that my name Kevin, and you immediately get compile time error. Why? As I already said, if you have anything having the same name as anything from any member variable or member method from that enclosing class, it shadows, right? You have this method with the same name as its toString method, where, well, runnable inherits from object. I mean, any object, eventually, if you just follows that inheritance hierarchy, then at the top it has object, right? And object has toString method. So every object in Java inherits from object class, right? So it has toString method. If you don't declare anything, then it's from object class, right? So it has that toString method. So runnable has toString, and that means it shadows any toString method in this app2 class. But this one takes parameter. It's not just the toString that object has. Object's toString method is toString without any parameter, just like this, right? This one, well, it has same name, but it takes one parameter. It doesn't matter. If you have the same name, it shadows. Okay? If you have anything with the same name, method same, runnable has any method which has the same name as the any member method, then it shadows that method. Any variable, local variable, or any variable of the same name, it shadows that member variable, or that non-local variable to this runnable. Okay, so it shadows that. And to print out, to use that toString method, you should do it this, right, like that. Okay, you need to use qualified name. And then what happens, it doesn't matter how many parameters you put there. So for example, I have another toString method. This is instance member method, and I put here name and another thing number, and here boolean is okay. Then what it does is hello, then let's just put them together. Okay, so here name plus equals plus number and comma is okay, then plus is okay, right? And what do I get? Number plus cannot be, okay, yeah, this one should be lowercase. All right, okay, if I do that, and if I want to use that, I cannot do this. As I said, this, the toString method of this runnable shadows that toString. Doesn't matter how many parameters it takes. It takes 3 parameters or 1 parameter or no parameter, it doesn't matter. It shadows every single toString method in this app2 class. Doesn't matter it's static or instance member variable, it shadows. So I do this true. Well, I cannot call that, it shadows. So to use that, I have to do this, because that's instance member variable. I have to do this now. Okay, like that. So it's verbose again, okay. So what about lambda expression? So here, if I want to use that, what I need to do, well, I just need to do this, Kevin, and the other one I'll call that instance member variable as well, like this. All right, run it. Oh, let's call toString as well. So I can call anything from this app2 class without any hassle. Yeah, you can see I'm app2. Hello Kevin. Kevin equals 1 is okay, true. All right. So that's difference between an anonymous class and lambda expression, right? This is in any way much more concise. All right. Okay. So let's talk about the other difference. So there are two big differences. One is this, and the other one is something else. So let's just talk about that. Is it in the, okay, not there. All right. So actually, before I explain the other difference, I think I'd better give you some example of race conditions mentioned here. So what I'm going to do is create another method called test race condition, and I'm going to call that here. Right, inside this method, what I want to have is a list of integer. So and okay, I have a list of integer from 1 to 20, and I want to print out, you know, every single integer stored in that list. So I just use lambda expression with this for each method and print out like that. Run it. As expected, you know, I got 20 integers from 1 to 20. Now what I want to do is I want to calculate the sum of every single element, every single integer stored in that list. So what I can do is probably something like this, right? I need to declare a new variable to store the sum. And inside this lambda expression, what I need to do is sum plus equals I. But I cannot do that because, as I already said, to make this no local variable to lambda expression accessible by this lambda expression, this no local variable has to be final or effectively final. Which means I cannot mutate that sum. Then here I try to mutate sum, so this doesn't work. And how can you solve this problem? Let's just think about what we did, you know, before Java 8 when we had the same problem with anonymous class object and you know, non-local variable. What we did was this kind of trick. Everyone knows this, right? So instead of having int variable, you can have an int array, and it has only single element there, and I can just use that like that. Print out result, and yep, I got expected result 210. But you know, here I don't have any race condition because, well, there are no multiple threads accessing sum and modified. So to simulate the race condition, what I need to do is I need to use parallel stream. So don't worry about parallel stream. Don't worry about this parallel stream. You know, I'll give you the details when I explain about stream API. So for now, what you need to know is if you just, you know, call parallel stream, you can have parallelization. So under the hood, it uses Java's fork join framework, which is Java's implementation of divide and conquer algorithm. So you know, one big problem can be broken down into several smaller problems recursively. Then multiple threads, you know, work on those several smaller problems, so you can get the result, you know, quicker. Especially, you know, when your computer has a multi-core processor. All right. But you know, the number of elements stored in the list has to be big enough, you know, because if the number of elements stored in the list is not that big, then you know, the dividing and merging them together takes longer than actual computation, right? Anyway, so that fork join framework is designed to maximize use of available core. So you know, you can get real benefit when you have multi-core processor, and but you know, that fork join framework is good. Problem is, you know, you have to worry about how to divide that, you know, that single one big problem in, you know, down into several, right? So here that's done by this, you know, Java's API, so you don't need to worry about that. And okay, so I have the same code, but now I have the parallel computing. What happens? See what happens? Run it. What? Now I just got 189 instead of 210. Okay, run it again. Sorry, run it again. Now 210. Run it again. 191. So as you can see, you don't get expected result every time, right? So just to see more clearly, I want to repeat it 10 times. Actually, Java 8 has better way to repeat same operation many times, but you know, I'm just using the old way, and I'll explain the new way later when I explain that, you know, stream API. Oh, okay. As I said, Lambda expression is lexically scoped, so I cannot use same variable name as the enclosing scope, so I need to change this to count. Okay, run it. See, it's not consistent. Okay, you get unexpected result. That's exactly what may happen when you have a race condition. So multiple threads access a single resource and modify it, and then you may get unexpected result. We have kind of two problems here. So you know, primitive types in Java, except long and double, are atomic, which means any operation you know, runs on that primitive types is atomic, right? But problem here is this one is not atomic, because you know, you are not just, you know, putting some value to that int variable or taking some value from int variable. Here you take that value from int variable and then add another int value, then put it back. So it's not just single operation. So that you know, atomicity of that int primitive type doesn't help. So that's one problem. So it has to be thread safe. Another problem is you know, when multiple threads access single element, and if you know, mutation happens by one thread, and then the updated result may not be available to the other threads, right? So one thread updated this, you know, some value, right? And then the other threads may or may not get the same updated result. So we have two problems. One is thread safety, the other one is concurrency. So you know, thread safety to protect, you know, that operation and make that atomic, so that, you know, no more than one thread update that, you know, single value at a time. And the other problem is make that change available to the other, so concurrency, right? Protect and make it available. Two problems. To solve the problem and think about, you know, old imperative way, how can you solve the problem? Well, I'll give some example of that solution. So here, what I'm gonna do is just copy and paste that, and instead of using this int array, what I can use is something guarantees atomicity, which is, well, atomic integer. So I can use this atomic integer, okay? And here, what I need to do is I need to call the method inside the atomic integer, which is add and get. So it does that, you know, take value from that atomic integer and add this I, and then return that value at the same time. So it guarantees the atomicity, and I just print it out. So run it. If you compare the results, okay, the first one still unstable. Okay, you don't always get the expected result. Here always get the correct expected result. Okay, that's good. The problem is you mutate the state of this atomic integer, which means you can easily make mistake. I mean, mutation means, you know, easier to introduce a bug, because you may do something like this by mistake, right? What's the result then? Like that. right? Because you mutate something, when you mutate the state of some element, some object stays outside the lambda expression, right? So how can you have a better way, better and safer way? Let's just try declarative programming using I'll explain the details later, but using the stream API actually here. So you don't need any mutation anymore, so just get rid of this atomic integer, and here instead of using this for each loop and mutate something, what I can now do is, well, this stream has method called reduce. There are 3, but I'm going to use this one. What it does is, okay, if you just put some initial value and second one, okay, first parameter takes initial value, second parameter takes accumulator, which is I think that's binary operator. This is a functional interface. So what it does is it takes same type of 2 values, 2 parameters, and then returns same type of 1 value. Okay, so what happens is it takes the initial value and use it as the first parameter of this binary operator, and then it takes the first element from that list and use as a second parameter of this function. Then here it does some computation as you specified, and then returns that value, returns the result, and use it as the first parameter of this function again, and then that time it uses the second element as the second parameter, and then it does some computation again, result is used as the first parameter again, and then this time it takes third element and used it as the second parameter of this function until it runs out of element, right? So which means in this case it's actually that computation depends on what you want. Here I want to get the sum, which means I need to add all the integer stored in the every single integer int value stored in this list. So what I need to do is I just need to simply do I1 plus I2, and what happens is first time okay, what is wrong? Yeah, semicolon. All right, I forgot about this now. So first time it takes 0 as the first parameter of that function, right? And then it takes the first element and use it as the second parameter. And here what happens is this I1 is 0, right? And then I2 is 1, right? 0 and 1, and add them, and result would be 1, and it uses this result as the first parameter, and this time it takes second element and use it as the second parameter of this function. So second time this first value would be result of that previous one, so it's 1 plus this 2, so result should be 3, and then it uses 3 as the first parameter, and this time it takes third element as the second parameter, which means previous result plus third element 3. Okay, so third computation result should be 6, right? And then use this 6 as the first parameter, and then this time it takes fourth element as the second parameter, so fourth computation should be 6 plus 4, which means 10, and it uses 10 as the first parameter. So it keeps going on until it finishes, it runs out of that element, so it finishes computation of every single element stored in this list. So at the end I should get the sum of every single integer stored in this list. Okay, so let's run it. Here I need to get store result somewhere, so no mutation, just final variable like that. Run it. Okay, as you can see, the first one is still unstable. Okay, second one gives you the correct same result, and third one, new way, gives you correct, same results. Okay, so this way is better because there is no mutation outside this lambda expression, right? You do not assign anything, or you obviously assigned that result, but other than that, you have no assignment statement here, right? And you don't mutate anything, so this one is you may have much more robust code, so you can here you have more chance to introduce a bug because you mutate something, first one and second one, right? So here you don't mutate anything, right? So much less chance to introduce any bug. All right, so now let's talk about the other big difference between lambda expressions and anonymous class. To see the difference, I think we'd better check out the bytecode generated by Java compiler. So what I'm gonna do here is create another class called app3, and here I'm gonna create a runnable object first using anonymous class. So what it does is just prints out hello, and why don't I make it even closer? So just like before, it has int number 10, and then I'm going to create another runnable object, this time using lambda expression, so it does exactly same as that anonymous class. Now let's have a look at the class files generated by Java compiler. So as you can see, it has app3.class for this app3 class, and here is app3.1.class for this runnable anonymous class. So whenever you use anonymous class, Java compiler creates an extra class file for that anonymous class. But so if I comment it out, save it, then that file just disappeared, right? But I cannot see any class file for lambda expression. So you may think there must be class for lambda expression in this app3.class. So, well, let's figure it out by looking at bytecode using Java P. It doesn't look like it has any class for lambda, but it has invoke dynamic and static method called lambda$0. So what is going on here is that it turns out, unlike anonymous class, there is no class for lambda expression in compile time, but it has something called, lambda, that called something called lambda recipe, which has information of how to create an object using the lambda expression. Okay, so why does it not have compile time class, and it has recipe to recipe explaining how to create lambda object? Think about this. Once any bytecode is set for that lambda expression, okay, we have this class bytecode for lambda expression, then later on Oracle comes up with better idea to handle lambda expression. They cannot really do anything about it because that class bytecode is used by already used by millions and millions of applications, right? So instead of having fixed compile time class, it has recipe that explains how to create lambda object. The benefit it can have is once Oracle releases better JVM, then you can get performance benefit for free even without any recompilation. So it's like that. Think about this. You have a recipe and you give it to different chefs, then you may get the same dishes from all those chefs, but taste might be slightly different, or in some case completely different. And if a restaurant hires better chef, then you may get the same dish with much better taste. Just like that, once Oracle releases better JVM, then you can get performance benefit for free. So that's kind of benefit you can have with this way. So so what happens is, when Java compiler compiles this Lambda expression and it desugars that Lambda body to static method, so something like this. So if it can create static method, and it does, and if it cannot, then for example it captures something from instance, then it creates instance method. So, and the method signature looks like a Lambda body, and it doesn't have any parameter, but in this case it captures this non-local variable number, so it adds that number here. Then method body should be exactly the same, like that, right? So if you have a look at the bytecode, this is what I just wrote, and then this is what Java compiler generated. It looks really similar, right? Okay, this is desugared Lambda body, and as I said, if it captures anything from instance, for example, I'll just use the same one to show you the difference. So exactly same thing, but if it captures something from instance like this, instance number 100, and instead of number, it captures the instance number from this F3 instance. And if you have a look at the bytecode, this time, see, this is old one, old static method, and this is the one I just wrote, this Lambda expression, which captures instance variable. Because it captures instance variable, this method is instance method. Okay, so let's forget about it now. And so it desugars the method body, and it uses new features added to Java 7 called method handle. So with method handle you can reuse this method many times. So you can you can store reference to method in method handle, then method handle can be stored in constant pool, which means if you want to reuse the method again, you just need to take it out from constant pool, which is really fast. So in Lambda recipe, this is not actual Lambda recipe, but just something that you can you can get some idea of what it looks like. So you have a desugared method, and then the Lambda recipe has information of that desugared method. So that object created using Lambda expression can use this method. It's actually the implementation of actual Lambda expression, and it has also information of the Lambda expression, the type. In this case it's runnable, and it also has information of dynamic arguments, which is that number in this case, which captures non-local variable. Okay, it has that information, and it has also something called bootstrap. And so what happens is, when JVM gets this invoke dynamic, then it uses bootstrap method, which is in this case for Lambda is called Lambda meta factory. So it asks Lambda meta factory what to do, and it it figures out what to do, and then it returns call site. And with the linked call site, JVM can get object generated for that Lambda expression. So that Lambda meta factory creates class and creates an object and returns it. And once that call site is linked, then next time JVM gets the same, then here, and then it doesn't need to ask the bootstrap method to, you know, handle the lambda expression, but it can just you know, use that call site, which means if lambda expression doesn't capture anything, for example, predicate of the integer and something like this. Okay, this predicate looks like this, so it doesn't capture anything, right? It doesn't have any state. In that case, what this does is that call site just reuse previously created lambda expression. So using that object created by lambda expression would be really fast, alright? But if you do the same thing with anonymous class object, for example, like that, then whenever JVM gets here, then you know, it gets new object. Alright, if that visits 10 times, you know, the 10 new objects would be created. Here it will reuse the same object previously created. So first time that bootstrap method lambda method factory to link the call site, you know, there is cost for that linkage to call site. Once it gets call site, and then next time JVM visits and use the call site, you know, over and over again, right? So that call site might be, you know, the constructor to that created, I mean the class created by this bootstrap method, or it can be anything. It depends on, you know, the implementation of Java virtual machine. So that's implementation detail of Java virtual machine. And as I said, you know, Oracle releases better version of Java virtual machine, then you can get performance benefit. And it's not decided, you know, you cannot figure out in compile time. So by the time you watch this video, and what happens after, you know, that lambda meta factory is called, then the result might be different. You know, now it's just accessing the constructor of a class created by this lambda meta factory, but when it's released something else, like, you know, I heard that Oracle is doing some kind of experiment to have a wrapper class for every single functional interface. So there will be only one class for, you know, each functional interface, and then what it has is it you know, passes method handle so that it can have, you know, kind of dynamic behavior for same class. Then if it works better, then, you know, they can change it, then it's different, right? So anyway, that's what is going on here, and that's the benefit you can have, and that's why it's different from, you know, the lambda expression is different from anonymous class.